So first thing, I'm grading the FRQs right now. I'm almost done. Out of 21 points, the highest score so far is 17. And that person is sitting in this classroom in a green shirt. So far. I still got third period to finish the second FRQ. I will I will tomorrow have we don't have it for last year, but the year before they have the score breakdown, what the total score, the raw score on the actual AP exam, what raw score you needed to get in order to get a 1, 2, 3, 4, 5. I'm pretty sure it was about 60% and above, you get a 5. So there's a rather large curve on the AP Physics 1 exam. But to do well enough, though, you're going to have to, I'm not going to say you specifically, but in grading the FRQs, they didn't cover, obviously, all the topics that we've covered so far, but there's a lot of very basic things that people are not getting. And so I just want to draw your attention because it's pretty obvious that a lot of you didn't do this. But I assigned flipping physics review videos for you to watch. Right? And you probably should have watched them because it definitely would have helped. Basic things like centripetal acceleration, angular momentum, basic concepts that you needed to know for the 2 FRQs. And then so that's on the module for April 19th. On April 20th, I put a bunch of review material, all the notes that we've done for all the units that we did this year, a bunch of multiple choice questions with solutions, a bunch of FRQs with solutions. It's obvious that not too many people look through any of that either. So you got 2 days here. You got 2 days. You probably should have been doing this before now. But anyway, that's on the 19th and the 20th. Lots of review material. I know you got a bunch of tests coming up. But whenever I put the scores in for the mock exam, there'll be major grades, and I'm going to obviously curve them, so I won't be able to put those grades into Skyward until I finish grading the FRQs. But yeah, those will be going in shortly. But don't focus on the grades right now. Focus on getting the content, getting the concepts down. So what I'm going to do today is go over, because it is a secure test, I'm not able to go over the actual problems, the actual multiple choice questions themselves specifically, but I can address, the difficulties with them with regard to the concepts that's covered by each FRQ. So what I did, I went through second period and third period. That's you guys in the next period. And I listed all the problems where a large percentage of students missed them. And then I circled in green the ones that were common to both classes. You guys didn't have as many problems as third period, so I shouldn't say problems, but yeah. Third period struggled a little more on the multiple choice, it looks like. So that's what we're going to do today. I'm just going to go through the concepts that it seemed like more people messed up on or need a little refresher on, specific refresher. So please pay attention. These are things that you can drastically increase your score if you just pay attention to what I go over now, because these are the things that most of the people lost points on the multiple choice question portion. Okay, and obviously that should correlate pretty well with FRQs. If you understand the concepts well enough, you should be able to do pretty well in the multiple choice and the free response. Okay. So when an object is orbiting another object, say we got a planet, some mass planet, and we got a moon or a satellite, okay, in a circular orbit. Most people were okay with how to determine the acceleration of that object. The acceleration is centripetal acceleration. Most people seem to do well with that, but then there's a question of, does the planet exert a torque on the satellite? And you kind of want to say yes because you see it rotating, right? But remember, torque. You take the force on the object. In this case, it would be a gravitational force. And then you have to show the position of that object with the position vector r. And torque is force times lever arm or position vector, lever arm, times the sine of the angle between them. The angle between R and the force of gravity is what? 0. The angle, 0 or 180 degrees. 0 or 180, same thing. Well, not the same thing, but you get the same result. Sine of 180 is 0. Therefore, there is no torque. And that's why the angular velocity doesn't change in a circular orbit. Okay. Even if this was an elliptical orbit, at all instances even if it wasn't even orbiting, if it was moving through a hyperbola because it's not gravitationally bound, the position vector and the gravitational force will always be 180 degrees from each other. And so there's never any torque on a satellite that's in orbit around another body. Okay. So no torque. No torque in this kind of a situation.
So what was the answer was like no torque, and then what was it was like, and the force was
well, it's either yes, there is a torque, or no, there isn't a torque. And then one of them says the force isn't big enough, essentially, which doesn't make sense. Because it doesn't matter how far away this guy is. It's going to be on the other side of the observable universe. You'd calculate, theoretically, a force. Right? Theoretically, every object in the universe exerts a force on you. The observable universe. All right. Any questions about that? All right. All right, so there's a question and this one is commonly missed, regardless of what physics class you take. This is just something that is kind of weird. Students kind of struggle with because they get the V squared with kinetic energy and then mgh for potential energy. But if I have a pendulum that I release from the horizontal and it moves down this way, at what point in that motion is the kinetic energy of the object equal to the potential energy of the object? Well, if we know that gravitational potential energy is mgh, and here it's all gravitational potential, here it's all kinetic, so no gravitational potential, and the potential energy is a function of the height, directly proportional to the height. If I start at some height h, well, I'm going to have half of the potential energy once I'm at height h over 2. Right? Make sense? And when I'm at height h over 2, this is maybe right about there. When I'm at height h over 2, I'm still way over here, right? So that angle is definitely less than 45 degrees. Right? So if you need to draw a little diagram, right? If you're having trouble visualizing some stuff like this, just draw a little diagram. This one's kind of, because what do most people want to say? Most people say it's going to be when it's exactly 45 degrees. But when that angle is 45 degrees, this height is definitely less than half of the starting height. Right. Cool beans? All right. So that one's pretty commonly missed. All right, force versus time graphs. If I have a force versus time graph, and let's say it looks something like this, but then it stops and it's like something like that. Force versus time, when I have this kind of a graph, this area means something. The area, and if it's horizontal, it's easy to see. It's this force here, times this time interval, right? This height times that base. That's an area. And so that's going to be the force times the time. I'll say this is T1, because then we're going to go to T2. T1. And then the area here would be, let's call that force 1. This is force 1. This would be force 2. This area will be force 2 times time 2. But it is in the negative quadrant. We have a negative force, so we have a negative area. I know you can't have negative area, but the area here isn't something in physical reality. It represents something in physical reality. And that's the product of a force and a time interval. And if you remember, and on the formula sheet, you know that the F delta T, force times the time interval, is the impulse. And that's equivalent to the change in momentum, right? So in this first interval, we got a force that's acting over a certain time interval, changing the object's momentum. So it's speeding up because it's positive. We have a positive delta P, that means we're gaining speed. And then at T1, then we have a force in the negative direction, so we're actually going to slow down. Remember, the impulse momentum theorem just tells you the same thing as Newton's second law. It's just a different way of looking at it, in many ways much more convenient in many situations. And so we're going to slow down a little bit, but because this area is so much smaller than that one, we're still going to have a net positive delta P, net positive change of momentum. Okay. And I'll just throw this out again. Newton's first definition of force, algebraically, is delta P over delta T. He did that. He invented the concept of momentum, the mathematical concept of momentum, before he even formulated the laws. That's what led to his laws of motion. We learn it the opposite way, and then whenever you learn calculus, the triangles turn to lowercase d's, which just means a really tiny change of momentum over a really tiny time interval. Okay. So it's force versus time graph. If you have force versus time, be thinking impulse and momentum. Force versus displacement graphs, that's when you have work, right? Force is acting over a certain distance, that's work. But a force is acting over a certain time interval, you should be thinking impulse momentum. Obviously, they're related. We're just looking at things differently based on the available information. Okay. You're feeling it? You're having fun? Learning a lot? All right, what's the next one? Okay, this one, we'll talk about this one again whenever we look at the free response questions tomorrow. But if I have an amusement park ride, and there's a table on it, and there's an object or whatever, if you're sitting on the seat in there, and we got an object right there, and we want to find the normal force exerted on the object, the net force, and it's moving in a circle. So let me indicate that. We're moving in a circle here. We have an angular velocity, meaning we are moving in a circle. And this is fresh because I was grading the FRQ's last period for this particular problem. A lot of students are saying the normal force is equal to the weight force here. A lot of students are saying that. If that was true, then the object would continue moving this way, right? In a straight line at constant speed. If it's moving in a circle, that requires a net force, a net centripetal force, which means whatever force is upward must be larger than the downward force. Right? It's probably not going to be a lot larger in a Ferris wheel, but it's got to be larger. It's got to be larger, and that's why if you're going fast through one of these, you feel like you're being pushed down in the seat real hard at the bottom because that normal force is really, really big. And so Newton's third law says, well, you push down on the seat just as much. But yeah, you need that net force to point towards the center of the circle in order to continue moving in a circle. Okay. And then if you had to determine what that normal force is based on some given information, you would just use Newton's second law, Newton said the net centrifugal force here, always call towards the center of the circle the positive direction. So I have the normal force minus mg equals mass times centrifugal acceleration. You can always, this is on the formula sheet, centrifugal acceleration is speed squared over r. I'm assuming you're all taking AP Physics C next year. We'll actually derive that next year. For this year, you just need to take my word for it. And then, so we can substitute that in there if we want, but that's how you calculate the normal force. Cool beans. So that was a very commonly missed problem on the multiple choice section. And the FRQ is obviously very similar. The second FRQ is very similar. So yeah, make sure you get that. If you're moving in a circle, the acceleration is not zero. If you're moving in a circle, the net force has to point towards the center. So if you have multiple forces, the ones pointing towards the center have to overcome the ones that are pointing away from the center. Okay? And if they don't, then the object moves in a straight line with constant speed. Okay. That's like when you're swinging something around on the end of a string. The centripetal force, the tension force, has to be greater than any other force because the instant you cut off the tension, it flies off in a straight line, right? Because now you don't have that net centripetal force. All right. Moving on. Any questions? You can stop me at any point here. Okay. That was 16. Let's go to 18. Motion graphs. So let's say that we had a projectile that was launched with an initial velocity pointing downward. And we want to graph. I'm not saying this is a specific question here, but I'm just saying we want to graph the vertical component of the velocity and the displacement. So I want to graph displacement, our position, x versus t. That's just our position versus time graph, and our vertical velocity. And it's just a sketch, so you don't need numbers or anything. Notice it says vertical component there. What would the horizontal component graph look like? For velocity, what would the horizontal? Straight line. Yeah. Because it would be positive, right? So we'll draw that one too. Position. What about the position versus time graph?
It's like this.
Yeah. It starts, we assume, at 0. But then as the projectile moves towards the ground, its position in the x direction is obviously increasing. Okay. The vertical velocity starts negative. It has an initial velocity that's negative. So you'd actually start the graph there. And it increases, right? Because it's accelerating. It has the acceleration due to gravity, which points down. So that vector is going to increase in the negative direction. So it's got to look like this. And then, like Yale said, the horizontal velocity versus time. Well, there's no acceleration in the horizontal direction. So we have a constant velocity. If right is defined as the positive direction, then it would just be a horizontal line. Cool beans? Whew. All right. Remember, stop me at any time if you need clarification on anything. Please. All right. Let's say there's something kind of like that. Let's say I have a mass m, frictionless surface, and then an object of mass 2m. mass m is moving towards mass 2m with some speed v naught. And then they collide. And they collide inelastically. Inelastic means they stick. Inelastic is sticky. Elastic is bouncy. So they stick together and then move as a single object. And hopefully we can surmise that that final velocity would be smaller than it was initially. Okay. And let's say we want to compare the kinetic energy here to the kinetic energy here. Well, the kinetic energy we know is 1/2 mv squared. So the initial kinetic energy in this system, let's say they use I's instead of knots. Say they use I's. Kinetic energy here is going to be 1/2 m v naught squared. Okay. This guy's not moving. He's got no kinetic energy. After the collision, the final kinetic energy is going to be 1/2. Now I got mass 3m. 1/2 times 3m times this speed squared. And remember, when you like find a ratio of kinetic energies before and after, momenta before and after, then you're really looking for a number. A ratio gives you just a number, a unitless number generally. But our problem here is that v is not the same as v naught. Like obviously the m's are going to cancel when I do a ratio here. But the v's aren't. And so I left something out, something that should jump to your mind immediately anytime you see a collision. So whenever you think collisions, what should your brain jump to immediately? Because chances are it's what you're going to have to use. Momentum. Okay, we'll write that right. Collisions. Think momentum. Specifically, momentum conservation. Because remember, in any collision, no matter what happens, momentum is always conserved. Always conserved. Kinetic energy isn't, mechanical energy isn't. In fact, I guarantee you that the final kinetic energy here is going to be less than the initial kinetic energy. All right, so if I want to do momentum, the initial momentum equals the final momentum. The initial momentum is just mv naught. Final momentum is 3m times final velocity. Everyone brought mass to the party, and so that final v, this is why I'm doing this. That final v I know is going to be 1/3 of the initial v. And that allows me to make that substitution in for that v, and then when I do the ratio, when I take the ratio here, then all the variables cancel and I'm just left with numbers. So if you're like me, you'd be very careful here. I have 1/2 times 3m times v naught over 3 squared. That's 1/2 times 3m times v naught squared over 9. But then that obviously cancels. So that would be 1/6 mv naught squared. Right? Now when I look at these two, if the question said something like, how much, I can't word it the same, how much energy was lost? Right? How much energy was lost in the collision? How much mechanical energy was lost due to being converted to heat, sound, other things? Well, it's just the difference between these, right? So if I want to know how much energy was lost, I'd say the change in kinetic energy, that's just going to be final 1/6 mv naught squared minus 1/2 mv naught squared, which is what? Negative 1/3. So we lost that much energy. Negative 1/2, 1/3 mv naught squared.
I'm pretty sure I put that as the answer, but I don't remember when I looked at it. I remember that answer, that question being
It wasn't worded like that. That's why. Yeah, it didn't say exactly that. It was worded slightly differently. So you did it right, but you probably just kind of misread what it was asking. Again, I can't talk specifically about what they specifically say. Just you knew what you were doing. Just read a little more carefully. And yeah. There's a lot of different ways they can ask. They can ask how much work was done by non-conservative forces. Because you might have answer choices that have Ki in them, right? So in that case, it would be like, well, what proportion, what fraction? And so let me go over that too. Let's say I have, this is another way of looking at it. Final kinetic energy, take the ratio. Final kinetic energy, 1/6 mv naught squared. Initial kinetic energy, 1/2 mv naught squared. Well, that's going to be 1/6 divided by 1/2 is 1/3. Yeah, 1/3. So I have Kf over Ki equals 1/3, or Kf equals 1/3 of Ki if I just multiply both sides by the initial kinetic energy. And so if that's the final kinetic energy, then that means 2/3 of the kinetic energy was lost, right? And so depending on how it's worded, just be careful. Just be careful, because I'm sure you knew what you were doing. You just kind of messed up with the wording of the question. Sound good? You having fun? I know you're having fun. Okay. This one was very, I think, missed by quite a few people. However, it was towards the end of the test, so that might be it. Let's say I have 2 blocks. And let's say we have an applied force pushing on M1. Say some applied force, Fa. And we want to draw a free body diagram for M2. The thing is that this force does not act on M2. Unless it's a field force like gravity or electricity, electromagnetic, or strong or weak nuclear, or gravitational, you must make contact in order to exert a force on an object. So yes, this force is applied to M1, but then M1 applies a force to M2, right? Right? So if I wanted to draw a free body diagram for M2, I would obviously have the wave force, M2G. Obviously, I'd have the normal force on M2, so I'll put Fn, 2. But then, and let's say that we're accelerating here. Well, let's say there's friction too. If there's friction, then I'm also going to have a left pointing friction force. Kinetic friction if the system's moving. But I'm probably at least moving to the right, or I have acceleration to the right, in which case I have to have a rightward force. But it's not the applied force. It would be the force coming from M1 on M2. It is M1 pushing on M2 in response to the applied force. Okay. And if they're accelerating, this must be larger. If they're not accelerating, if everything's moving at constant speed, then this needs to be the same size as the friction force. If they were already moving and now they're slowing down, then F1 on 2 needs to be smaller than the friction force. Right? But there was only one answer choice in this particular question that made sense. Okay. Also, This wasn't asked about on the test, but it's good to know. What about the free body diagram for M1? For M1, I will have a rightward applied force. I'll obviously have an M1G and a normal force one. And obviously the weight force and the normal force, they have to be the same because the blocks aren't accelerating up or down. Is that it though? I guarantee you a lot of students would leave that.
No.
What other force is it?
Well, there's
Yeah, and I didn't say that, but force 1 on 2 is literally a normal force that M1 exerts on 2. But then Newton's third law says if M1 exerts force on M2 that way, M2 needs to exert a force on M1 in the opposite direction. So I would have the force of object 2 on 1, but these two forces are exactly the same.
and friction.
And friction, that's what I said. That's not what I said, but thank you for reminding me. Alright? Don't free body diagrams, guys. Don't lose points on those ones. Alright, those are the easy ones. Since we're on the subject of free body diagrams, on the FRQs, you don't want to lose points on free body diagrams because they're, again, those are the easier points. If I have a normal force this way and a weight force this way, you put FG if you want, or MG. But I know that the object is like accelerating up. I saw this. Centripetal force. Ooh. The normal force and mg combine to form the centripetal force. You never label a free body diagram with a force and label it centripetal. Any force can be centripetal. Any force.
Would you put static friction on there?
I'm thinking about a specific problem that that I don't have up here.
Yeah.
Yeah, there wouldn't be any friction in the one I'm thinking about.
Does it involve a bug?
We'll talk about it tomorrow. We'll talk about that tomorrow. Also, I saw this on not too many, but don't make this mistake. This is a guaranteed way to lose points. Some people had this for tangential velocity on their free body diagram. Guaranteed way to lose points. Okay. If it's not a force, it doesn't belong on a free body diagram. Okay. You only put forces. And if it's like that problem where they got a dot and you got to draw the forces on the dot, you don't even put components on those ones. Okay. If you need to do components, you draw another quick little sketch next to it. But if you got a dot or a circle or a box and they say label this thing with all the forces that act on the thing, then you got to make sure that that's all you do. All right? Okay. All right. Remember the equation for torque. Let's say I have a rotating object and I have a force here. Maybe not even a rotating object, but just I have an object with a force acting there. And then a force acting there. And we know the magnitudes of those forces, F2 is twice the magnitude of F1. And let's say that F2 makes an angle of theta with the horizontal 30. So it makes it an angle of 30 degrees. And we want to know whether this disk, or whatever it happens to be, looks like a disk, is in rotational equilibrium. We want to know if the net torque is 0. Okay. Well, I know. You gotta do the lever arms. It's gonna be R. It's gonna be R. Okay. And I know the definition for torque. I'll do this for 1. It's gonna be F1 times R, same lever arms for both, times the sine of the angle between them. What's the angle between F1 and R? 90 degrees. So it's going to be, if this is sine 90, the sine of 90 is? 1. So it's just F1 times R. Right? Alright, what about torque 2? Torque 2 is going to be F2 R sine of the angle theta. But I know that F2 is 2 times F1. So I can plug 2 F1 in for that, times R. What's the angle between R and F2? 150. It's 150 or 30, right? And it doesn't matter whether we use 150 degrees or 30 degrees, right? So I think technically they say that the angle here would be 30 degrees, but it doesn't matter. It doesn't matter because sines of supplementary angles are the same. So you can use the 30 or the 150 and you get the same thing. However, on the formula sheet, the table of values, right, that you're given on the formula sheet, they give you the trig functions evaluated for certain common angles. You can write on the back if you need to. Still got the formula sheet, right? Yes. Okay. So yeah, if you look on the back of the formula sheet, they give you the trigonometric values for the common angles. On the multiple choice question, it's always going to be those angles. They're not going to give you any other angles. And very rarely, honestly, on the FRQs, do I see them giving you any other angles other than your 30, 45, 60, all that good stuff. Anyway, so the sine of 30, even if you did not looking at the formula sheet, if you're in pre-cal, what's the sine of 30? 1 half. If you're in pre-cal, you should know that at this point. So that's going to be 2 times F1 times R times 1 half. Or just F1 times R. What I've left out here, though, is our sign convention, right? Unless you've defined your coordinate system otherwise. A torque that wants to cause counterclockwise rotation, we define as positive, the positive direction. So the torque 1 would be positive F1R. The torque due to force 2 is going to want to cause rotation in the opposite direction. So it's got to have an opposite sign. F2 would want to cause clockwise rotation, and by convention we call that the negative direction. And so we get net torque, or we get a torque of negative F1R, giving us a net torque of what? What's the net torque? 0. And the object is in rotational equilibrium. If somehow these forces were able to be maintained in their current locations and direction, but this object wasn't fixed at that point, we would still be in rotational equilibrium, but we wouldn't be in translational equilibrium, right? We'd have a net force. How do I figure out the direction of the net force? Well, I just do vector addition. Remember vector addition? We did that several years ago. I add one vector to the other by lining them up tip to tail. The net force here I'll draw in purple. This wasn't part of the problem, but it's good to know. The net force on this object would actually cause it to accelerate down this way. Although if these were like strings attached to it, it would be pretty much impossible. It would be very difficult to keep them acting at the same angle at the same location. But if somehow you could manage that, then it would definitely not be in translational equilibrium, but it would be in rotational equilibrium. So those are the ones that both classes miss quite a bit on. The rest of these, either you guys struggled more than third period or third period struggled more than you. But it doesn't really matter. It's still stuff you got to know. So let's say at time t equals 0, we have a position of 5 meters, and we have a velocity of 5 meters per second in the negative x direction. And we have an acceleration that is constant. Let's say it's approximately 2 meters per second squared in the positive x direction. How do I find, and this is my initial position, my initial velocity, a constant acceleration, and I want to know what my final position is going to be? It's kinematics, right? Yeah, I was surprised. Now, sometimes they give you a range of acceleration. They say the acceleration is somewhere between these two values, and then they say, okay, given that range of values, what's the range of potential final positions, right? Which just means you need to do two kinematics, or pick one right in the middle, and then although that might lead to it could be this one or that one. So yeah, you do it, just do it twice, and that's the beauty of writing the equations first and not just plugging in values first, because then you can just plug in another number real quick into your answer, right? So which kinematic equation do I use? I'm given at time t equals 0, but I'm given no other information about time. So we're going to use kinematic equation number 3, which says that wait a minute. Oh, maybe that's why this one was tricky. Because if I use the equation, my brain immediately goes to x equals x naught plus v naught t plus 1/2 at squared. But then I realize I don't have the time, right? So what I can do, initial velocity acceleration. What I can do is use another kinematic equation, say final velocity equals initial velocity plus acceleration times time. No, I don't want that one. Why am I struggling here?
Well, it's saying like at t equals 0, so like it's saying like at t equals 0, all that is true. So why can't you use kinematic equation number 2? Because it's just saying at the time.
Because this time is not going to be 0. That's the elapsed time. That's the elapsed time. You could, Mr. P has his 4 kinematic equations. You could use that other one. I'm just seeing how you can get there with what's given on the formula sheet. You would need to combine. Oh yeah, this is kind of annoying. Plus a v and v squared equals v naught squared plus 2a x minus x naught. And this one's gross. This one's nasty, unless I'm overthinking it. Because I'm thinking we need to. Did I read this right? Hold on. Oh! If I knew how to edit videos, I would have edited that part out. Sorry, guys at home. Yeah. Which of the following gives a possible range of the position of the cart? T equals 1 second. You get a phone call?
Yeah, that was a spam call.
Oh. Aren't they always? So yeah, we have a time. So my bad. So yes, definitely kinematic equation number 2. Sorry about that. X naught plus v naught t plus 1/2 at squared. Yeah, and then just plug and solve. It's already solved for what we're asked to solve for. Just make sure that that v naught has got to be negative. The acceleration would be positive. So it's really moving this way, but it's got a positive acceleration that way. So it's going to be slowing down. And then if there's enough time, it'll reverse direction and start picking up speed in the other direction. Whew! Sorry about that.
Yeah, I thought I got that one wrong because you were saying like when you were doing it, I was like,
But you did get it right then? Okay, good. My bad. All right.
I'm just fine. You keep asking. Guess we'll never know.
Okay.
Alright. You can think that. We should never do that.
All right, so this one we actually briefly mentioned, or I briefly mentioned, but it wasn't common to both classes, so I didn't do this one. But this is just a note. Let's say I have a planet and a satellite. Where's my satellite? In orbit around the Earth. Common mistake. They give you the orbital altitude. Orbital, are we out here at 13?
Yeah.
Yes. An orbital altitude.
Is the AP classroom thing, is that new